Okay, hello everyone. This is, I guess, it's week 12 out of 14 weeks. We have about 3 weeks to go. You know, um, let's enjoy it until the end. And I am still debating whether I should have the last Friday, whether I should have a lecture on that day or not, or I should just let you guys enjoy it and then do whatever the teaching evaluation form for me and stuff like that. We will see. And also, I will get the second dose right before that. So if I'm okay, then I can probably teach or discuss with you guys a little bit or some things. Um, Anyway, let's see. Maybe your peers are coming a bit late today. Um, yeah, so maybe let's wait for one more minute. Any questions or concerns or anything you want to discuss with me before we start? Okay. Yeah. So roughly speaking, you see that the Pierce barrier occurs from the fact that people are curious about orbits of infinite amount of time, and from there it was telling us that essentially, one of the key points. So actually, many key points we have been proving was that even going from x to y in an orbit of infinite amount of time or nearly infinite amount of time, no matter how much time it takes, the cost is still being finite, and that is quite remarkable, right? You can go in all various different ways. um, so the cost is still finite, right? We have proved that this is the cost of going from x to y in an um, infinite amount of time, essentially. uh, so what was remarkable was that we proved that age is finite. There's a clear bout, but I'm omitting it now. Age is Lipschitz in both variable, and you have age satisfy the triangle inequality. So in a way, it's sort of like nearly a distance, but it doesn't have the symmetric properties, and the zero properties everywhere. So you would have that age of x is greater than equal to zero. And age of xy plus age of yz is greater than equals to age of xz. Okay. Again, let me say this is age is not a distance in general, a metric distance in general, as we don't know if going from x to y is same as going from y to x, and if age of x equal to 0, then it implies that x equal to 0. Again, it's also uh what did I say? No, this is not correct. What I said, if we always have h of x equal to 0 for all x, right? But it's nearly a metric distance, and you can see actually that from today we can use it to define further important information. And one of the very important point we proved last time was that if x is in the projected matter set, you would have h of x equal to 0. In other words, if you are in the projected matter set, it costs nothing for you to go in a loop of infinite amount of time, right? You know, if you go in 0 time, then going from x to x is always costing you 0 cost. But you have to go in a loop of infinite amount of time, so that's not easy at all. And that was a major achievement that we proved last time. Although I mean I wouldn't say that it's too hard, but it's something that we have been building things up on. And that was the important point we proved. And then that was the first part that I give a quick recap here. The second point I want to give you a quick review is that this is an important result in itself. And then sometimes you're going to use it, maybe not too much, but I mean, it depends, right? I mean, maybe it might be useful in your research or in some other things, I don't know. So last time I drew like M0 was a periodic orbit. Well, that's fine, whatever. So you consider M tutor of 0 as a matter set, and then you take a neighborhood around it, right? You just draw a tiny or big neighborhood around it, doesn't matter. It can be big in some places. So you would let V is a neighborhood containing the matter set, right? And what we proved is a weak attractor result. So what it tells us is that if you have an orbit of length long enough, so this is gamma 0, gamma t is somewhere here. If the length is long enough and the time t depending on v, right? So it really depends on, we need to choose a neighborhood first, right? And then we can find a big time t, because this is a compactness result, as I said. It remains still also an open problem to quantify this result. And as I said, I mean, we are not just making up the questions. In my opinion, quantitative results in large time average or in all of those questions are very important, because they in turn can give us natural applications to the study of ergodic theory of PDE. So I mean, so all of these things I have been presented to you are more like I have been presenting to you are more like qualitative results. And it would be great if someone comes up with a systematic way to look into those problems, or one of those problems, in a more qualitative and more completely different viewpoint. Okay. So what it says is that if you need to have a long enough time to go from gamma 0 to gamma t, then the orbit somehow is going to come into into the neighborhood, right? It's not staying totally inside the neighborhood, but it has to get into the neighborhood at some places. Okay, so that was sort of a weak attractor. I mean, this is in my view result, right? It's just not saying that you're gonna get all the way inside the neighborhood, because the result is strong in the sense that you can choose gamma 0 and gamma t, the endpoint, to be wherever you want, right? Not just, they don't have to satisfy anything. They can just be any you want. But if the length that you travel is long enough, it has to sort of somehow dip inside and get out or something. Right, so you would have some gamma s inside V, gamma s dot inside V. Okay, so now today we're gonna define the Albrecht set. This is another important set in the theory. And let me say it right away that the projected matter set, this is surely defined by matter, is a subset of the Albrecht set. Okay, the Albrecht set is defined by Fathe. Albrecht is a French physicist, if I remember it correctly. So early he has some results on the sort of like 2D modelings of particle systems, and is corresponding to the so-called Aubrey matter theory in 2D. But typically, I mean, Aubrey didn't work on this theory, and he actually has no ideas about Aubrey matter theories or the Aubrey set. Actually, I have never met Aubrey, but some people who have met Aubrey asked him, do you know what are the sets? And he said he has no idea. I mean, this is mainly defined by Fateh, but it's, it's fun. Um, and the Aubrey set is this is, we are looking it into the Aubrey set. We are looking into it by in the dynamical system viewpoint. There's a totally different and very rigorous and interesting PD viewpoint that we can look into it without using any dynamics at all. I don't have time to tell you because there's just too many. Okay, so the Aubrey set is rather natural. I mean, like, okay, so how do we define the Aubrey set? Earlier we have seen, I mean, I mentioned here, right? I mean, we have going in a loop is always costing you non-negative cost, right? And we have said that we don't know if it's a distance because we don't know whether h of xx is equal to 0 for all x. But we know that if we are in the matter set, then that projected matter set, then clearly going a loop from x to x in an infinite amount of time is costing us nothing. So a natural way to think about it and to come up with this definition is that we want to see, I mean, what are the missing points, right? So so we define the Aubrey set to be exactly collecting all possible points so that going from x to x is costing us 0, right? So that's exactly the Aubrey set. So this is so clearly from the definition one can see that again the projected matter set is a subset of the Aubrey set, right? Just a definition. And in general, this is actually a subset of the torus. And in general, I mean, it's very easy in various examples that the Aubrey set is not that big. Is a subset of the strict subset of the torus. Okay, so and how should I say it? And there are examples in which we have the matter set is a strict subset of the Aubrey set. Okay, but in general, okay, but generically, people believe that the matter set is equal to the Aubrey set. Again, generically. I don't know the status of proving this result up to now. There are some results, but I mean, there are sort of mismatches here and there. But generically, people believe the matter set is the same as the Aubrey set. But you will see. Okay. So let's take it gentle today. We're gonna talk about the Aubrey set, and you can see that it's actually not too hard to imagine about the Aubrey set. And many of my friends who are working more on dynamics, they say that they like this definition of the Aubrey set because it's really geometric. what it tells you is that you have, this is a point X and we have axis in the orbit set. If you can go just around in loops, right? If you can go in loop from here to here, uh, that is costing you like epsilon amount of energy, or I mean, you can choose to go in a different loops. And what it just tells us that is that going in loops from X to X uh, uh, for a large amount in a large amount of time costs us almost nothing. Okay, and they really like this definition of the orbit set. It's just real geometric, right? I mean, you can imagine that again, either like earlier lecture in the matter sets, you hop in the uh, backward characteristics, you get a free ride from X to some point really close to X and you hop back. Or you can imagine that, you know, you're going in the loops in which you are sort of like traveling around you know, the parts that you pay essentially zero along the way, right? So those are kind of like the rest places, right? You know, sort of like going there. And then we are describing exactly that and more, a bit more in a more, you know, intuitive way in those results that I'm describing to you. Okay, so let's do that. So we have the following equivalent. The first thing is that if X is in the orbit set, is equivalent to the second point that you can find a sequence of continuous piecewise C1 curve starting and ending at X, so that the cost going to zero. I mean, the second point is kind of obvious. It's just from definition, right? That exactly I just told you. Um, and the third point is also obvious. Is if you go in a sequence of minimizing extremal curves, gamma k, with time going to infinity, then the minimizing extremal curves is sort of giving you the action on that is going to zero. So the proof is very obvious. Let me just say it. So the above proposition can be deduced right away from the definition, right, of the orbit set. In fact, you know, again, maybe let me just write so that you have h of xx equals to 0 is equivalent to the fact that there is a sequence tk going to infinity, so that you have h of tk xx plus c naught of tk going to 0, right? Because I'm not worried about the other bound, right? I mean, it's this action functional going from x to itself is always non-negative, so so that's why it's equivalent to this statement, and this is equivalent to the fact that I can find a sequence. Maybe I'm gonna use a different notion. So eta k. Uh, well, I mean, let me just write. Let me just write the last statement. There's just a sequence gamma k, which is, you know, so you're given a fixed time tk, right? And then you're given the beginning and the end point, so you can run the calculus of variation problem, right? So you can find a minimizer directly without even going to the second step. Mapping to Tn, gamma k 0 equals to gamma k of tk equals to x, and gamma k is minimizing the action functional, right? L gamma k dot ds plus C0 of tk. Okay, so and surely this action function are going to 0. That's it. Nothing more than that. Okay. And what is interesting is the next result. Okay, so the next result, the theorem here. So the theorem, this theorem gives us a new characterization of the Aubrey set. Okay. Why is it new? I mean, it is in the earlier result, right? I mean, in the definition of the Peirce barriers, we would need to take the let the time going to infinity, right? But this new characterization tells us that actually we don't need to take the time going to infinity. We can just fix any time delta greater than 0. Okay. Again, we cannot allow the time to be 0. If the time was 0, then going from any point to itself would gives you 0 cost, right? So so I would say that we really need to have some positive fixed time delta greater than 0 to start with. Okay. Again, depending on the problems, but here we are talking about going in loops and going to some positive amount of time. So I don't want to allow my time to be 0, right? And hence it would be natural to start with some fixed positive amount of time. And this new result is really interesting because again, it's not hard, but it's really interesting because it tells us that X is in a Aubrey set if and only if that for any fixed time delta, I don't need to let t goes to infinity now. I just need to say that the infimum of the action functional, again, everything is standard. I just need to require that for time greater than delta or greater than equals to delta is equal to 0. So the infimum of all the action functional, if we go above certain threshold, certain amount of time, if this infimum is 0, then X is in Aubrey set and vice versa. Okay. Let me pause here to see if you have questions or concerns up to this point. Any question or concern? Okay. Good. So then if there's no question, then let me start. Again, the proof is essentially very simple, but again, it's quite geometric. And as you said, I mean, some of my friends who are top experts in weak cam theory, they said that they love this kind of, geometric intuition. The first thing is obvious, right? One direction should be obvious. Which one is it? Yeah, the implications, the first implication should be obvious, right? So what color should I use? So the proof, this directions is obvious or standard. Why? Because I did mention again here that if you have X in the Aubrey set, then you would have this box, right? You would have that you can find a sequence of loops with time tk going to infinity in such a way that the cost, right, is going to 0, right? And because our infimum is taken, our infimum among all action functional is taken for all loops with t greater than delta, right? And this one should be 0 because those tks are surely greater than delta, and infimum of that is giving us 0. That's obvious. So what is interesting and geometric is this direction. So this is not hard, but quite intuitive. intuitive. I'm just gonna describe to you by drawing. I did draw it here already, but let me draw it again. And again, I mean, in geometry, there's a notion for this. Again, I mean, for me, it just so you use the definition, right? So you can find, like, let's say for any whatever. So okay, I'm writing it in a fancy way later, but uh, let's say that you take epsilon greater than 0, right? Then you can find a curve gamma with t greater than delta, such that the action on gamma, I mean the normalized action, gives you the cos is less than epsilon, right? So you can find one curve, one loop that having the action less than epsilon. Okay? Then if you want to go for the point here is that I only know t greater than equals to delta. I don't know if t is huge or t is just 10, right? I don't know if t is a billion or 10. But I mean, I can just keep going in loops, right? So once I have one curve like this, then you can just keep going in loops. So take gamma k to be k copies of gamma, right? So essentially you're creating more loops. This is one copies, and then make one copies, one more copies, and then one more, and then make k copies. So you would have gamma k essentially is k copies of gamma, and then you would have that I of gamma k is less than equals to k times epsilon, right? And for this gamma case, you can make the time now becoming k times t, which is greater than equals to k times delta. And then if you increase k, it can get the time can get to infinity as k goes to infinity, right? And that's the idea. That's just that. And again, in geometry, there's a fancy term for this. You can say that uh, did I write it down here? So the notion here, you can just say that gamma k is just k copies of gamma, or again, I mean, geometric analysis, you can say that gamma k is gamma with multiplicity k, multiplicity, right? And this is interesting and beautiful, because sometimes when you do blowing up, I mean in geometric analysis, when you do blowing up around singularities, then when you converge to the limit, you might converge to like one minimal surface, or you can converge to a minimal surface with multiplicity 2, 3, and blah blah blah. So this is sort of the same thing. It's one identical things, but you would realize many copies of that. Okay, but that's all what it is. So that's the idea. And yes, as I said, this is why my friends like it, because you can imagine in your mind, right? If you go in a loop, it doesn't cost you much, then you keep going in the loops, for as many times as you want, and then this still doesn't cost you much. Okay, all right. Of course, I mean, again, to make it more rigorous, you can write down, right? You just for hk, you can select t greater than delta and a curve and a closed loop, so that the cost you is less than 1 over k square. Again, just a rigorous way to write things down. And then you let gamma k be k copies of gamma. Yeah, I did write down here, gamma with multiplicity k, right? Then with the new time and with the new gamma k, you can have that, still the action function on gamma k is only at most 1 over k, right? Again, epsilon And okay, so and the time is going to infinity, so we are done. Yeah, so that's a beautiful result, and it tells us that you know so those two definitions of our set the Aubrey set are equivalent surely and can be introduced in any order. What I meant is that depending on the textbook or depending on the research paper, people can introduce one notion and say that it's equivalent to the other and vice versa. They are the same. And then there, I could say that there is another equivalent definition. And this is in a PD definition. Actually, there can be two, but the PD definition can be really different. It looks totally different, but it turns out that eventually that they're the same. But again, I mean, there are just too many, so I don't know if I have time to do this. Okay. Any question for me up to this point? Question, concerns, remarks? Okay. Yeah, again, I mean, up to this point, I feel like that I haven't, you know, so far I haven't got a lot of technical glitches, and I'm quite happy. You know, we have been going really to according to the plan, and actually we're gonna eventually, I mean, we have a few more lectures to go, and then eventually we're gonna be able to cover basically the whole Fati's book or a little bit more based on, I mean, I'll give you some PD viewpoints, but okay. And this is the remark that, as I mentioned a few times already, this is corresponding to the so-called Manis conjecture, right? That it's a natural question. I mean, I remember when I knew about this, I also asked this question. I didn't know that it was a Manis conjecture, but eventually, I mean, it's a natural thing to ask, right? Because you would go for an infinite amount of time to reach to the infimum is zero, right? The natural question is that can you find a curve of finite time so that you have the cost is zero, right? So this question is actually corresponding to the so-called that can you find, maybe it should it could be more, maybe it could be easier to answer this question compared to the Manis conjecture. The Manis conjecture said that generically there's only one periodic orbit, but my question here can be simpler, right? You can allow for more orbits, but the question is very simple, that can you find so generically, I should say generically first, a periodic orbit in the manner in the orbit set, right? Again, you can have many orbits, I don't care, but I just asked, can you find one periodic orbit? And you know, this is not known. I naively asked this question quite a while ago, and I still couldn't find a way to answer that in the general setting. Okay. Anyway. Yeah, this is again dynamics in the generic sense. In the generic sense, is very different from PD. I mean, like you have to design things very smartly. You have to sort of like add a tiny perturbation in a good way and control everything. So it's quite different from PD, right? You cares about only one or a few, um, uh, you know, uh, orbits, and then trying to correct those orbits, and it's really sort of a different regime compared to all kind of PDs in which you try to find estimates, you try to prove, find properties of solutions using different techniques. But I mean, this is really cool. I mentioned to you a lot of stuffs, but I mean, keep them in your mind. Who knows, right? You can, you can surely, I mean, prove them uh, sometimes, I guess. Okay, so now this is the example that I want to end the so the this in this example I want to end our discussion for today. Is the example in which I have so here we would have that the Aubrey set equals to the projected matter set. I'm okay in this example. I mentioned it right away so that we are not um, uh, you know we are clear. Okay, so the example is always the classical mechanics Hamiltonian. This is the case that we know the best. Okay, and then the Lagrangian is 1/2 v square minus the potential energy, and the projected matter set was the set of all points y in x, so that I have v of y equals to c naught, in this case the max of the potential energy. Okay. And the point here is that I want to find out with you what are the points in the Aubrey set, right? So in this case, actually, we can find, those are the periodic orbits. You can just find. So this is gamma. This is a point. So this is a point x. That is in this point x, such that v of x is the maximum value, right? Okay, so you take this point and you just define your loop or whatever you want. It's exactly this constant function, right? So you define gamma s to be x for all s in R, whatever you want. Okay, right? Then if you define it this way, you would see that, I mean, what would be your action function going from 0 to t, L of gamma s, gamma dot of s, ds plus c0 times t, right? Just compute it. This is integral from 0 to t, L of gamma s is x, gamma dot is 0, ds plus c0 t, right? And Lx0, when v is 0, it's just minus a v, right? And you are staying, essentially at the point at which that you have the value is the maximum, right? So this gonna gives you minus c naught t plus c naught t, right? So that's 0. Okay. So I mean, the loop I'm doing here is just that I'm staying put, right? So this is just stay put. Whatever. Okay. So if I'm doing it that way, if I'm staying put, then clearly I would have that this would imply that x is in the Aubrey set as well, right? Of course, I mean, I'm doing nothing because earlier we have already shown that the matter set is a subset of the Aubrey set, but I'm just redoing it so that you see that this loop is quite weird, right? We are staying put. Okay. So that's the first thing. The second thing, I'm gonna ask you to do it so I'm gonna post one more set of homework problems, I mean maybe 3 or something problems, so that you can just do and submit it again. I mean, once you are done with submission, you're done. I mean, that's a requirement for the class. Surely I'm gonna have a look into that, but This is a topic class. So yeah, so please remember to do that. So what I'm gonna show, discuss with you a little bit, and then I ask you to do it in your homework problem, is that if X is not in the matter set, projected matter set, and also X is not in the orbit set in this case, right? Um, again, then with that we can conclude that the orbit set is the same as the matter set here. Okay, so let's discuss it intuitively what's going on. Okay, so I have maybe those are the points. Again, I'm just do a schematic picture. I'm not, this is truly not true in general, but so let's say that you have points in the, those are the points in the matter sets. Okay, M0. Okay. So maybe again those are surely the maximum points of the, or maybe there's also a line of the maximum arc max of V, right, of the potential energy. So M0 is set. It's the arc max of V. Okay. Now, if you take a point X here that is not in the arc-max of of V, right, and you can see what's going on. So what would be h of XX in this case, right? It's not easy to compute it actually. At least I know that at X, right, we know at least that L of XV is 1/2 of V squared uh, minus V of X. Okay, this is greater than equals to minus V of X, right? And minus V of X is still greater than minus C naught, right? So so what should I say? So this is still greater than equals to minus C naught plus some theta, where theta is nothing but C naught minus Vx. It's greater than 0. Okay, so what it meant is that, whatever you are doing here, the action functional of u at this point is gonna be always greater than equals to minus of C naught plus theta. And if you want to compute, if you're going in a loop from X to X, right, L of XV d no, if you are in a loop, L of gamma dot of ds plus C naught t, or maybe let me write this way. Ds, right? If you're going in a loop, then clearly, I mean, if you are wandering around X, let's take a neighborhood of X here. You're wandering around here. If this were your loop, go here and going back. Okay, whatever. Okay, if you're wandering in a loop, then there are some parts of the curve needs to stay in the yellow neighborhood of X, right? And in the yellow neighborhood of X, this cost is going to be greater than equals to theta over 2 or something like that for a certain amount of time, for some time. You would need to do a little bit of computations, but then you can show that no matter what, this is going to be greater than equals to some constant, call it not theta, yeah, theta naught is greater than 0 or something like that. So yeah, so that's what you need to show, and it's clear, right? I mean, again, actually we don't know in general what would be the peer barriers of XX, because if you go in a infinite amount of time, if you keep going, outside of the projected matter sets, it's going to be very costly. So naturally, let me copy this picture. Again, this is just a very schematic picture. Naturally, I can imagine that probably the best way to do is that you're gonna go from here. If you need to go for an infinite amount of time, you can go to a point, a rest point, right? At that rest point, you can stay put as forever as you want, okay? And then, you need to circle back, okay? So it's still gonna cost you some amount of energy or cost, but it's gonna be finite because of this. You can just go and hop on some place to rest forever and then hop back, okay? Yeah, but clearly that is gonna tells you that actual x-axis is greater than 0. Right, so let me end here. It's quite simple, quite geometric. For this example, for in the general case, it's quite complicated, but questions, concerns? Yeah, so sounds good. As I said, I mean, this is our 12th week out of 14 weeks. And then my plan is that to teach until Wednesday of the last week. And on Friday, I'm still debating whether what should we do. I mean, I'm leaning toward the option of letting we just skip that class on that day, and you can use that date to do the evaluation form for me or whatever, and maybe finishing some other problems. As I said, I mean, the only requirement for the class is that you do the 2 sets of problems. They are not graded. They are asked you. They are there so that you can do and understand things deeper. This is a very, very interesting topic. You can see that with lots of open questions. It's a 20 years old, 30 years old subject. It's hard, but you know, you know, it's interesting. Or it gives you a set of tools. Maybe later on you can plug in and use it for different purposes. Yeah. So there's one more example on the Aubrey and Mather set. You can see the so if you want to have a let me finish here. So if you want to have a further readings, and again check the headline and generalize examples in my book. They are really interesting. In 3D or Hygge, you can understand also all the, in that example, you can understand all the Aubrey and Mather sets, and they're very tiny. They're just 3 lines in the whole box, 3 lines, non-intersecting lines perpendicular to each other. And it gives you the sense that those sets are amazing, but they are too tiny. I mean, right. So thank you all. Again, stay strong. You have to be TAs, graders. Imagine that, I'm also trying to do countdown, like, so by May we are done and we have time for other stuffs, and the weather is getting better. So, okay, thank you and see you on Wednesday. Bye for now.